So maybe we can get started. So I thought that I would just introduce Hiro, who's going to be giving you the tutorial on the Calypso, which is a brand new spherical shell dynamo model that Hiro is the architect of. It was donated to CIG last September and is now available on CIG website that you can all download after this workshop, and you can sort of run it on your machines. This is a code that's designed to run on some of the largest supercomputing facilities in the country, as well as on your laptop as well. The kind of problems that you can do depend on which of those two machines that you use. I would say, and this is something that Hiro wouldn't said, but Hiro probably has more experience writing dynamo modeling code than I would say anyone else on the planet. So he's done this sort of pseudo-spectral technique, which he's going to describe today. When he was a graduate student, he did a fully spectral model, and as a postdoc, he developed a model based on finite element methods. And so again, I think no one has the depth and breadth of experience in terms of doing this as Hiro, so it seemed very appropriate that he would actually lead us through this discussion. So Hiro, thanks very much.
You're welcome. Yeah, thanks, Bruce. Oh yeah, I don't need mic, nah. So today I have a tutorial for the Calypso. So Calypso is yes, Bruce has introduced, so it's a numerical dynamo code for the rotating spherical shell, and so it's work with a parallel computer platform. Does it work? And with MPI, and so it has a large flexibility for the parameterization, and it also has a capability for the various kind of output, and it also very, very big documents. And question is, what can Calypso do? So it's a magnet hydrodynamics simulation in a rotating spherical shell. You've already seen it in this movie in John Arnold's talks. It's evolution of radial magnetic field at the quantum boundary. And so it also has a capability of the W diffusive convection model driving by the thermal and the compositional buoyancy. Here's the evolution of the, now it shows the pressure, but the evolution of the right element at the 320 kilometers from the quantum boundary. And so the right element go entrained by the convection in this model at the convection curves. And so it's a latest feature. So here's a Bruce performed model. So the model with Bruce performance. We can. It has a capability to set the thermal heterogeneity at the inner core boundary or outer core boundary. It's a snapshot of the temperature at the ICB and the quantum boundary. So it's a little bit hard to see any characteristics in a convective current, but we can find an effect of the temperature anomaly by taking a time average. So today's goal of the tutorial. So let's try to run some rotating convection simulation using a Calypso, and so I'll walk through a parameter file for the Calypso and so understand this, how to describe the model for the Calypso. And then finally, so it's a very similar tutorial as aspect. So we run a simulation with a different Rayleigh number and make a scaling relation between kinetic energy and Nusselt number. But we have dynamic simulation has a little bit of problem for this tutorial because Calypso can only perform with three-dimensional simulation. It's super heavy. There is a reason. So Cowling found Cowling theorem in 33. So if flow and magnetic field is two-dimensional. For the outer core, axisymmetric is a good example. Dynamo never works. So we can sustain the dynamos in such simple flow and magnetic field pattern. Then to obtain self-consistent dynamo, we need three-dimensional simulation model. That's the reason why we haven't gotten a successful dynamo simulation by 95, which is Gary Grassmeyer's paper and Akira Kage's paper. And Calypso only accepts a three-dimensional model. So then, unfortunately, today I gave up to treat the magnetic field. We solve rotating convection in the spherical shell. So we solve the Navier-Stokes equation with thermal buoyancy and Coriolis force. And so I will solve the energy equation without the heat source. And so the conservation mass is also solved in a system. And geometry is pretty simple. We pick up the outer core and sometimes inner core in the simulation domain and consider Ri to be inner core radius, Ro to be in outer core radius, and we often set the length scale using the thickness of the outer core. And we don't consider any electricity, and so the system is complete perfect sphere and rotate with a constant angular velocity. I don't want. Oh yeah, it comes. So then, the most suitable coordinate system is spherical coordinate. So we solve the system with radial direction and theta meridional direction and phi zonal direction, and then we need to discretize the system with this coordinate system, and we also have to use spherical harmonics expansion. So we already seen this spherical harmonics twice or three times. So field pattern can decomposited by this spherical harmonics with a degree L or latitude order and order M. So easiest consideration is M represent zonal wave number in the longitudinal direction. So the pattern is getting smaller and smaller in phi direction with increasing the M, and it's a little bit weird. L minus M represents the meridional wave number. So then, if L minus M equals 0, no pattern, no change in direction at the meridional direction, and so the pattern is getting smaller and smaller in a meridional direction. And so we also describe the spatial resolution with this truncation degree of spherical harmonics. So, and we have a home page for the Calypso with here. I wonder if we can access the home page by clicking the PDF. And we also have a mailing list. Now it's a little bit quiet. And we also have a wiki. Then, if we have some trouble, problem, or question, we can communicate using this mailing list or wiki. So let's start. Have you already started a virtual machine? Okay. So we need. And so now Bruce and Ian and Nick will help if if you have some problem to run code. And so Sean, thanks for operating on the screen. So there are 3 steps, very simple. One is preparation, preprocessing, and we need it made indexing and specular and data communications table for parallel computations. And then we run a simulation using this data, and then finally we'll make post-processing. So, there's no slide what we do now. So we'll make scaling plots, and so we also look full field pattern using this purview. Anyway, so
Following what Sean's doing on the
yeah.
so we're getting to the right direction.
Yes. So first, so now on the terminals, all data and programs are in tutorial Calypso directory. And there are 2 directories in this folder. So one is a convection program for this tutorial, and so we don't use it, but I also leave an example for an MH dynamo program up here. And so can you go to this directory with a convection really something XXX. So then in this directory, so there should be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 file and directories. Everyone, did everyone get? Okay, let's go to the next. And so all the stuff in this directory. There are 2 files for the data analysis using a GNU plot with a GNU extension GNU, and so there are 2 parameter files for Calypso, and there are 3 empty folders. Is that written with dark blue for the field listed and a little bit long name, and binaries, executable programs are writing with light blue. So everyone has these files? Probably everyone must have. Yeah.
It might be worth to say that the pre-processing is going to go into one of those directories.
Yes. So pre-processing indexing data should be in this SPH LM 23 blah, 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 directory.
Can I also make another comment?
Yep.
The name of the file, the name of that thing is related to the resolution.
Yes. So now I'll show the slides. Thanks. So first is a pre-processing process. So we use this file, gang SPH grid, and so this program uses control. Oh, order has changed in screen size. Control SPH, yeah, this guy. Control SPH shell. So, oh yes, I forgot. Sorry. Yeah. Oops. I fix here. Oh, you've already started. Yeah, go ahead. Yeah, okay, let's start now. So it's a screen capture of this program. When we start this program, it gives some messages on truncation degree, L max, and number of the grid for the radial, theta, and phi direction. And here's a parallelization information. Now all at once, and it's for a single process, one process data. So then, after running it, have you start? Can you run this program? Okay. It's not so. It doesn't need a long time, probably you got some, yeah, everyone laugh at the program is normally terminated message and getting back the console. And then, so all generated files are in this folder. So yes, sorry, I should leave it. So 23 indicates truncation degree. T36 indicates a number of the million of grid, and R48, 48 grid points with Chebyshev grid Chebyshev collocation points, and one subpolarization. But you can define this name in this control files, and you can choose any name as you want. And yeah, let's check so we can get right data in this to check this by checking this directory using ls sph lm 23t36 r48c1. If you too long, so using a tab key, so probably you can fill this directory name. And there are 5 files with in.0. So is anyone there? Is anyone who can't get? Anyone got? Great. Yeah. So now we can ready for the simulation. So again, it's 3-dimensional model. It takes a little bit longer time. Then we'll walk through this parameter file after starting the simulation. So for the simulation, we use a command with SPH, MHD. Yeah, can you show the LS again? Yeah, LS again. Yep, this binary. And so control this program, read control MHD and run simulation. So today, there are 3-dimensional numbers in the rotating convection problem. So Prandtl number, which is the ratio of the viscous diffusivity and thermal diffusivity, and Ekman number. So it's yeah.
This is just kind of a general. What is the lowest Ekman number you've been able to run?
That's a terrible question. So I don't have any good slides, but yes, as John mentioned in the lecture, length scale is getting smaller and smaller with decreasing Ekman number. So we need very high resolution to run very small Ekman number. In a Calypso, or I've tried to 1 times power 2 minus 5 with L equal 128. Truncation level to be 128. Yeah. Then we expect we can reduce more. We can use more low Ekman number such as 3 times 1 time part 6 or something like with 256 max 256 or 512. Yeah.
Can you remind those of us who don't do this very often what the range of Prandtl Ekman Rayleigh numbers are in Earth's core?
It's still far away. For example, Ekman number would be 10 power to minus 15 for the outer core if we consider molecular diffusivity, and Rayleigh number would be 10 power to 24 or 5, but probably, we are running it with a 10 power to 4th order, very small. Still, it's very, very far. Actual Earth parameter is far away. And Prandtl number. So it would be something like 0.1 or something like for the Earth. But yeah, Many people run a model with Prandtl number 1. Somewhat a simpler problem.
So if we were to run this program, what numbers should we use to not break the program?
Unfortunately, program only crash if you set something crazy number. That's what I can say.
But you don't know you can't tell me what a crazy number is.
We're going to give you a list of reasonable numbers.
Yeah, sorry. Yeah, sorry, I don't have such. Yeah, actually, I remember some feasible number, but I never made such table.
So I think a lot of the runs are going to be around 10 to the minus 4.
Yes, 10 power to minus 4 is the most popular number, with something like 32 or 62 cores. And we perform less than 10 power to minus 4 with hundreds cores. And the numbers ratio of buoyancy and diffusivity, probably John's expression would be more clever. So now, as I said, we run 5 different Rayleigh number and fix the Prandtl number to be 1 and the Ekman number to be 10 power to minus 3. Not yet.
So I think
We haven't started yet.
you should have the code running now, right?
No. I'll show slides where we should edit.
Can we run it just from the...
Are you running already? Probably that's something a default parameter with 10 power to 4. Okay, so now you run a simulation with this 10 power to 5.
Is that what we just did?
Huh?
Is that what we just did?
Actually, so that's something like a default parameter in this example. So you need to change. Oh, there's another slide. So it's something expected results with a Rayleigh number, the kinetic energy, and the dot is the results, and line is scaling resolution, expected solution. Then let's see. It will be explained in Friday's talk by Bruce.
So I think the plan is you guys are going to change the code.
Yes. That's a slide, and so now. Okay, then let's change Rayleigh number. Sean, can you open gedit?
It's the lowercase c on the file name.
Yeah, right. So parameter file control MHD is file. Yeah.
If we start changing the parameter file now, is that going to affect the current run, or does it read it in and then it's done?
Yes. Once it reads the initial and then no problem. Yeah. And so on the editor, so I found an option to display a line number, but probably you don't have. So line number is displayed at here, as Eric told in aspect tutorial. So has everyone opened a parameter file?
Yes.
Okay. Let's go to the line from 143 to 150. There's a block of the parameter dimensions numbers. So in a control file, I always set the block with starting the begin something name and end something name. And if there are more than 2 entries are there, so I set. So it's defined. The block is starting with the array name and number of entries, and So now there's a Prandtl number, Rayleigh number, Ekman number, and the outer curve radius on this field. So now we'll edit here. Everyone should know that. And unfortunately, we need a little bit shorter time step for this highest Rayleigh number. So if you're confident your computer is fast, choose this guy. Yeah. And
Can I do this while running the previous run? Or is that
can you delete the dot output file with a dot dot?
it's still running? It's on like almost 2,000.
Oh, go ahead. Go ahead. So, has anyone chosen 70,000? Good.
Just like in the previous set, we need a little organization so that we make sure that all of those numbers get covered.
Yeah. Yeah.
And so
Has
maybe the way to do this is we can
raise the hands.
go through and then you show hands.
Yeah. So now you choose 70,000, and has anyone choose Luis run this parameter? Okay. And yeah. Has anyone choose 200,000? Good. And anyone choose 400? Good. And 1,000, great. And can you set 8,000? Oh, great. And so for this, something like the brave guys need a length of the time stepping. Originally, it was you've already changed. Originally, it was 2 times 10 power to 4 is a time step, length of the time step.
So for those of you that
Yeah.
want to do the most extreme case, so
Yeah.
only easy,
It's only for the extreme case. Ne?
change the 10 to the minus 4 to Louise.
But I don't
Everyone
know
else
if
can
kill this run. Should I be killing the run?
kill the run option.
Yeah.
Because there are going to be many other people that do.
Yeah. Yeah.
So I need to.
Yeah.
Maybe we
But
can sort of get organized in the sense of let us know actually once you've got your input file adjusted.
yeah,
So it's just that one file, right?
Just the one.
one file.
The Rayleigh number the only thing we're changing?
Yeah. Today we only need to change the Rayleigh number, and this is a time step for the highest Rayleigh number case. Ne? So reduce the time stepping 2 times 10 power to 4 to 1 times 10 power to 4, 10 power to minus 4, and the length of time stepping from 4,000 to 8,000. Ne? Yeah.
Once we have this, can we go ahead and start running?
Yes. Yes. So then, has everyone changed the parameters? Okay.
We'll just take a minute. We'll let everybody get their.
Yeah.
So can you just put the Rayleigh numbers back up again?
Yep.
So maybe again, just make sure that we get adequate representation. So who's doing 7 times 10 to the minus 4? We got a couple.
Yep.
Okay, we got a bunch doing 10 to the 5.
Yep.
2 times 10 to the 5. Got a couple. Okay, 4 times 10 to the 5. Great. Okay, and then only Louise. Oh.
Yeah.
Computer's not that.
Okay. Those of you who are doing the 8, you just want to make that one change to the time step, make it a little bit shorter, and
Yeah.
number of steps.
Twice. Yeah. Yes. Yes. So we can get some cost to the state. Ne? After simulation. We can check the evolution of the kinetic energy after that. After that. Oh, sorry, Luis?
I'm sorry.
Oh, yeah. Okay. Yeah. So then, so I've already shown the commands. It's a little bit different to start MPI programs from the single processor program. We need MPI run command first, and NP, which indicate the number of processors or processes, and so given a executable command out here. And here's an example for domain case. So probably if you run this command as is, so your program must stops. This example is for one domain. Then MPI run NP 1 SPH MHDs. That's how to run a program with MPI. Yep. So it's getting a little better. Can you see that? Probably. Yep. And once push return, so there are some small messages so to reading the data, and so some message for the coefficient of each terms. So has anyone have a problem? Yep.
I have a quick question. This number of processors, right?
Yes.
So if we have like a quad-core computer or something, should we have changed that to 4?
To do it, unfortunately, so you have to generate index data again for the pre-processing programs. So
Theoretically, if you have a quad-core
yeah, I always use 256 cores processes. Yeah. Yeah. So has everyone started the programs? Has anyone?
So I think the plan was that you guys would start the programs, and then Hiro would walk you through the input file to show you how you could do other processes and change it, give you the velocity and instructions, and then while your codes are running, because you're waiting for
Yeah.
15, 20 minutes, you can just show the organization of that file, right? So who hasn't actually launched their jobs? Anybody?
Has everyone started a job? Or has anyone having a problem?
Remind us how to launch the job again?
Right there, and NPI run.
Oh, MPI.
Yeah.
So what was the job that you ran on?
Largest number core I've tested with 32,000 core on Argon. Yes. Yeah, that's the largest case. But it's only in a moment, 10 or 100 steps. Not for yes, so to check the performance. Yeah. So something I always use a 512 cores for my research or productive runs. Typically, yeah. Yes. It depends on programs for the Dynamo, a few weeks. Yes.
How many time steps is that?
10 million time steps. Yeah. And for the summer convection, WDC convection program, so I performed one day for something like 400,000 steps or something like that. Yeah. Yeah. So some parts on non-magnetic case is much easier to run.
Typical natural convection code could be sort of tens of thousands of steps, maybe 100,000 steps.
Yeah.
And a lot of numerical dynamo models, it's really tens of millions.
Yeah.
And that's just because the
Response with the magnetic field is much slower than the convection. That's the reason. Yeah. Yeah. Typical case, we need 10 times more time steps for the dynamo than non-magnetic convection. Yeah. Yep.
As a rule
Yep.
of thumb, how many steps should I let it spin up for before I start reading?
Oh, to get in a steady state? Yeah, so today, it depends on parameter, but so for the non-magnetic case, yeah, 10,000 would be good indication. And so today I will show 4,000 or 8,000 steps. Yes, it's still okay.
So
Yeah.
if you were 10,000 steps, depending on your parameters, it could take anywhere from, let's say, like maybe half hour to like a few hours.
Yeah. Sometimes. Yes.
Or like, and depending on your
It depends on the resolution. And so for the WD physics case, time stepping is controlled by compositions. Then we need much more fine delta t and time stepping, more time stepping. So okay, we have enough time, plenty time to walk through the parameter file. One is input file for preprocessing, named control underscore SPH shell. Yep. Oh, you open a both file. Yep. So it consists of 3 blocks. One is for the file names, definition of the data file names, and next is parallelization information. Today I'll skip this block. And last part is definition of the spatial resolution. That's it for this pre-processing program. First block is probably I can skip it. So we need to define the parallelization this file, but first block is file names. Very simple. One is how many processes is using this run. Now we set only one process, and why I set the wrong name? Yes. Yes. Why I set the wrong name? It should be 23. So, as I said, I set spatial resolution as a directory name. It's given up here. So, set the directory name as SPHM23T3648 and .in. So, file name is given by this block. Then you can set any file name as you want by changing here. And so, next block will be, can you go to line 26, skip the polarization part. And number of grid control is, first block is a truncation level. It's a Lmax, so to represent the truncation level of the spectral harmonics. Now we set 23. And next is number of the grid for the horizontal direction, meridional direction, and zonal direction. We usually set 1.5 times the truncation level to be the number of grid of the meridional direction. Then 23, if we include the degree 0, there are 24 components. There are 24 degrees. Then 1.5 times would be 36. And so the number of the zonal grid is something simple, twice original zonal grid. So we explicitly define these numbers out of this block. And lastly, radial grid. So it's a little bit strange approach or definition for the dynamic community. We set a length scale by using the thickness of the shell, and we also define ratio of the radius of the inner core boundary to commutative boundary. So it's also typical number 0.35. So then by defining these two numbers, so we can calculate actual value of the inner core radius and the outer core radius. So in this case it will be 7/13 and 20/13. So we need to set the geometry by these two parameters. And so we also set the number of the radial grid. So I also deleted the grid data, but with 48 layers by this block. So that's it. So we can set the spatial resolution and the truncation level. We can make the tables. Then run a model with defining the control MHD. So first block is very similar. Yeah, title is almost same. Data file definition and number of subdomain, and so SMP course, it also has another parallelization, but skip here. Then that's what we defined in control SPH-MHD. Put the same name and set the name of generally starting file with spectral and field data output for the visualization data at this block. Yeah.
That is, if you have set up size of the grid, for example, and set up the main decomposition, once you create those files, you can run MHD over and over and over again using those same files. You don't need to do pre-processing once. If you change anything in your grid, the resolution or the decomposition, you need to regenerate that, probably put it into a slightly different name.
Yeah.
Which is why Hero's naming scheme is really good. It's very explicit about what it is and what it does.
Yeah. 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 Because I often forget what the resolution I set. Oops. So in a model, so we need to define what field we will treat. Today we will set the velocity, temperature, pressure for the thermal driven convection, and so now I always set the voltage T for the visualization. And so next column is a flag to output the visualization data. If you turn on, so this field is written in a data file. And if we set turn off, so the pressure won't output in field data. And here is another output for the time sequence data with the kinetic energy or average field, and it also same flag as on or off. So next block is on line 55. So we need to define what field should be evolved. Now, so we solve the evolution of the velocity and temperature. Then we restart here. Then for the dynamic problem, so I need to add the magnetic field on this block. Very step by step. And next is boundary conditions. So boundary conditions, there are temperature and velocity boundary conditions here. And so now there are three blocks for the boundary conditions, temperature boundary conditions. First item is a mode of the boundary condition. Fixed value, isotemperature, or fixed flux. And so next block is a place in a core of a commutative boundary. And so actual value is given in the last column. So now so set the hot 1.0 temperature to be in a core boundary and commutative boundary to be 0 everywhere. And for the velocity definition is also very similar. Set a non-slip boundary in a core boundary and also non-slip boundary at the commutative boundary. And so this case, honestly, I don't use these values, but we need it to set the same format as the temperature boundary conditions. It's a little bit limitation. And next block, what force shall we put in the model? Gravity and Coriolis for this case. And so now it supports the Lorentz force for dynamic problem, and for the WCDC model, so there's another item for the composite gravity, composite buoyancy. So probably this part is the most complicated, how to construct a normalization in a system. So here's a normalized governing equation, but I put 1. Usually, so we don't write this 1 on the equation, but probably it should be useful to describe how to set the parameter file, how to set the parameters. Here is an example on line 125 for viscosity and buoyancy term. So there's one at here, and so probably buoyancy term would be more easier to describe. There are three dimensional numbers to construct the buoyancy. 1 over R and Rayleigh number and Prandtl number. Then list these names at here. So questions for the buoyancy, we need three coefficients, R over 0, Rayleigh number, Prandtl number, and given a power of these coefficients at the next column. So 1 over R then it's -1, Rayleigh number is as is 1, Prandtl number is as is 1. So viscosity, there's not, so we have to define something, then give simple something like reserved value 1, which always substitute 1 at this coefficient, and power is also 1. So then these blocks are listed around these blocks to construct each terms of the governing equations. Yep.
One of the great things about this code is that there are many ways that you can non-dimensionalize equations. You choose different viscosities or kinematic efficiencies for time scales and that sort of thing. And what this allows you to do is choose a completely different set of scales, define different non-dimensional equations, and you can basically adapt your problem to exactly the scale. So this is for one specific scale.
Yeah. Yes. It's one example. Yeah. 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 Honestly, dynamic community, many people use different normalization for the papers. Yeah. Then so now this code accept many variable kind of normalizations. So that's a fair we've already seen. Once set the name of the dimensions number on the previous block, so we carry these name to here with the dimensionless control and given values for each parameters. So then, honestly, you can set any name. You can also set any name for these dimensions numbers parameters, but sorry, it's still case sensitive. Be careful to adjust set name with the capital and small characters. And then, so now we set the governing equations, so field to solve, and boundary conditions, dimensions numbers. So model is completely described. Then we set time stepping. Oh, sorry.
What is R0 again?
0?
Is that the core mental boundary or the interval? What is R0?
0?
RO?
RO? It's outer core radius. Yeah.
So again, I think the thing is that you take that distance, R0 is 1.5, and you subtract the radius of the airport, the gap will be exactly 1.
Okay.
Yeah.
Let's show it.
Actually, real number is 20 over 13. And inner core boundary is 7 over 13. Under this regime, inner core and outer core radius ratio to be 0.35. It's very close to the RC's aspect ratio.
But you don't have to do that either, right? You can change it if you want.
Yeah. We can change any size. Yeah. So here is also another block for time stepping. Now we start the simulation from time step 0 and to now it's 1,000 or 3,000, 4,000. And here is the increment for the average data or Nusselt number output. Something
Would you ever start at a time step that's not 0?
Actually, we can start from some different numbers. Yeah, I don't recommend to set minus negative number, but.
So why would you start at a time step other than 0?
So restarting the solution.
Restarting?
Yeah. But that case sometimes we start from reserved the programmed initial field or reading from the external file from the restart field. Yeah. Yes, because so yes, and so as I said, I often run simulation for a few weeks, but most of the cluster does not accept such a long job. I have to terminate the simulation for 1 day or 12 hours and start again. In that case, I change the initial step number when I stop the previous job. And so end step number is defined here. And so increment original time sequence data, then it's pretty fine. Restart data, we don't have to out so often because it's pretty big. Field data is also big, but a little bit more often. So we can set a different time increment for the data output. And unfortunately, time stepping is fixed, not variable steps. So we have to decide what length should be run. And so if there's no restarting data, so we also need to define initial time step. Now it's 0, very simple. So, I already know this slide for it, but I already told. So, and last thing is time sequence data. There are crazy number. It can output a crazy number of the data, but important thing, today's useful thing is volume average data and mean square data and Nusselt number. So this program output the history of the Nusselt number at inner core boundary and outer core boundary, and output the kinetic energy or other mean square data in file names with this file prefix. So, has anyone finished? How many steps are you going? So, still, my code is also 4,000. Oops, halfway. So let's see. Has everyone finished at 2,000 or 3,000? Something like. Already. Yeah, I'm a little bit afraid how it happens now. Yeah. Let's wait for and. Yeah.
A couple of maybe this was many slides ago.
Yes.
You showed the grid.
Yeah.
That you didn't know this on, but you had a couple of slides where you were showing the grid.
Finite element grids, something like here. Oops. Oh, no. Oh, is it good?
So near the poles, it's going to the grid goes to like disappear.
Yes. Yeah, everyone asks about it. So
To avoid like singularities.
actually, yes. So how slow my computer? Yep. Let's see. Yeah. So yeah, we always get this funny shape of the funny pipe at the pole. So we always use Gauss-Legendre points for the spectral harmonic expansion. So this point doesn't include the pole. And then I use this position. I also use this position for data output visualization. That's why still there's a tube at the pole. Yeah.
If you're using Gauss-Legendre, then that's a little misleading. It looks even, or is that just within elements, or because it looks evenly spaced there?
Oh, it's not equal completely. Yeah, but almost. Yeah, Yeah, I need double check how close to the gas point, giant point will be in a even space. Ne? Yeah.
The numerical model, or the domain of the numerical model, includes that central part. It's really only the visualization.
Actually, then the simulation also excludes it because no. Well, in a space. Yeah. Yes. In a spectral space, of course, it's included. Yes. That. Yeah. 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 Actually, so to put the data on a pole, we need a little bit special transform for the pole, the field of the pole. Yeah. So because on the original expression has 1 over sine theta, then it got infinity, then a little bit different. We need a little bit different expression for the square transform. Yeah. Yes. 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 Yep. Oh, actually, so now it supports two different FFT library. One is a FFTW, another is a FFT Yeah, usually so FFTW is pretty fast, but I don't include the source code of the FFTW in a package. Then, if someone has a problem to install it, so we can use the FFT pack. And Legendre it won't never change on the Legendre transform, but FFT is much faster than with the FFTW on the Intel processor. Yeah, we found it's not so fast on the power-based processor by the IBM. Yeah. But if we can specify which library you will use in a control file. But if we don't specify, so program compare which is faster in the beginning and choose one.
How are people doing as far as their solutions? Once the requisite number of steps to be done.
Yeah.
So I guess whose computer is still running?
Yeah.
So you need to talk to your advisors about getting faster.
Probably we can look at field data now.
Yes.
Yeah. So let's keep going, but let's check how field will be. I changed order, so probably we can check what files are there after finishing, but oops, you've already started. No, I'll swap now order now. I decided to use the preview first. So field data is stored in this field directory. So then, if your program is finished, so type ls field, and so you can find 17 files in this folder. And there are files with two kind of extension, pbtk and btk. So pbtk file is a parallel btk file which will use it. And this btk data is something like a segmented data. Then for the one domain, whole data is in this file, but if we run more than two processors, sometimes it only starts in northern hemisphere or southern hemisphere, then we need to read them. So please start preview with this icon. Clicking this icon. So probably you can start a preview during the simulation. Yeah. Yeah. And so to open some file, so that's partner Eric already walked through. Push the open button and choose the file. If we finish the simulation, we can find the out.8 PBDK in a field directory. Convection ready number field, and open this tab, and then so the larger case, more files should be written. Yes, please choose something latest file 8 or 76. Anyone is fine. Don't you have the data?
Not the
PBDK.
There's a little thing at the top with a plus sign.
Yeah, so you've already got it. Does it have this solid color?
So I think there's a problem with this one. I don't know if I put the thing.
Can you open it again?
So you can
Yeah, so then you can get some data. You can.
I can look at an earlier one.
Did you change it? Did you change time stepping?
Yeah, right.
But so kinetic energy getting none. What's wrong? What's wrong? Let's see. Can you go back to the time stepping? How about the ready number? Ready number is that's strange. That's strange. What's wrong?
I can open it.
Yeah, but this is can you open the files in work directory? Can you open the preview and push the open button, and go to the home directory and desktop work and no, sorry, it's not. And let's see, that's a different tutorial. Can you go back? Yeah, I learn all the stuff in the work. Calypso 800 and field and same thing. That's strange. Yeah. Why? Yeah. So can you open has anyone have a problem to open a file? Yeah. Yeah, so haven't you have any output? You've already opened it. Okay, you've already opened it. Yeah. And last is click the apply button, and we still have one problem on the preview. Sometimes on a screen is getting white. So we couldn't find this problem on a virtual box. But when it happens, always apply button to be in green. Then please click this guy. Then screen comes back something normal color. Is a normal color, Yeah. So yeah. Yeah. And now we get some ball and blue ball, and then if we look at the voltage, G component of voltage at the common boundary. Here's a more simpler case. So your case is more complex. You can get some field pattern on that. surface. Oh. Yes, so the pattern is getting more complex with increasing the Rayleigh number. Yeah.
Yeah, so I mean, the expectation is that this length scale, the characteristic length scale, will be the length of your domain, which is L, times Ekman to the 1/3. So you can sort of make expectations of how small the field is. The other complication is that when you drive the convection harder, you will also get smaller
Yeah.
field fields.
Yeah. So these are only examples. It's a case with 100,000 Rayleigh number to be 100,000. It's a 800,000 case. Ne? Yeah. But still, it's a. Can you see such structures? Let's look at something like a field dominated by the rotation by Taylor-Pladman theory. To do it, make a cross section, meridional section somewhere. Then so we can set some field pattern aligned with the rotation axis. Ne? Yep.
Okay, so if we want to do the cross section on vorticity.
So
What's that?
no, temperature doesn't show good.
Here again, remember, is kind of the swirl of clouds. So when John Arno was talking about those sort of helical convection columns, vorticity will be a nice way of illustrating those helical convection columns. Definitely vertical vorticity is the thing you want to select.
Yeah. So to make it, push the slice button with a 1, 2, 3, 4 from left, and yes, and push, and default is X normal. So now it makes it shows how to make the sections on the field, and then push the apply button, but it comes back to temperature now. Oh, does it keep now? Yeah. It always problems and it's always same temperature. Yeah. Yep. Push the slice.
Yeah, I'm sorry. Yeah.
Yeah.
The only thing I missed was
Okay. So after making a slice, please choose G component velocity again on the menu. Sorry. It always, I don't know why, but it's a problem. What's, oops. Yeah. And can you, does anyone have no problems? And if we can get this slice, so there are some funny bar here then, and you can change the direction of the slices with dragging this small tab. That's another option. Yeah. Yeah. Then please push the apply button.
I did, but is
But
there a way
still,
to keep it from going all yellow when you drag something around?
so it always getting yellow after dragging, so you have to click again and again.
Okay.
That's it's very sorry for it. Yeah. It's yep.
If they get NAN in the influx or the initial number,
Oh, did you also have?
Yes.
Yeah, that's problem.
Problem.
Yeah. Yeah.
Is that a problem with the solution or is it a problem with the?
Problem is in
Or is it a problem in the computation of the Nelson number? Oh my.
the initial number calculated right into it.
yes, right. Yeah, then problem is in the parameters. Yeah, Chan also has a problem then. Yeah. But yeah, actually, so So I tested it yesterday, but it got the right answer now. But
Did you change the time step from the small to time step? Because you're running 5 random.
the C, MHD. Let's see.
Inside it, it will go blank this time.
That's a
There's
strange.
basically a problem on the solution.
Yeah, I think so. Yeah. Anyway, so these parameters are almost limits of the
Okay, so the time step I used, let's see.
one.
Where did I go past it?
No more below now. It's far below.
Okay, so there's my real line number.
Yes. And
There's my number of time steps.
yes.
And then
That's same parameter. Should be okay. There's some problem in the. I'll need double check. So it one. So honestly, this results is what I got at this parameter regime. I need double check. Sorry for it.
are the lower real line number ones getting this, or just
No, it's only for the 8 times 10 power to 5 case.
So you can try it again and make the steps smaller.
Yeah.
So before you magnetic forces,
Huh?
what we assumed about magnetism just in the simulation?
It's in a dynamo. We use a magnet hydrodynamics approximation. It's somewhat approximation for a very large scale field. So we assume of course we assume neutrality and force balance between collisions between ions and electrons and electric force, so which represent the current density. And then we solve the momentum equation for the whole material.
No, there's in this calculation there's no magnetism.
Yeah.
There is no magnetism.
No magnetism.
But can you add magnetism? Of course.
Yes.
If you want.
Yes.
Okay.
Yes.
So what Hiro was saying was that the force on a moving charge is on the moving charge, right? But that force gets transferred to the cores of the atoms, basically.
Yeah.
So it's J cross B is the magnetic force.
Yeah.
But the point is that you turned off magnetic fields.
Yeah.
So the induction equation out of problems. In the control file, you involve velocity, temperature, and magnetic fields. You've got an MHD problem now.
Yeah.
And Hiro, in the example files, with the MHD example, has set up some input files for doing the control of the MHD problem.
So, yep.
Can I use this code to calculate the dynamics of maximum ocean and turn off the magnetism?
Magma.
The influence of inertia in a magma ocean is very important, whereas the effects of inertia in this calculation
Yes.
are pointless. So magma ocean is really turbulent in the normal sense that inertial nonlinearity is important.
Was the
But-
Rossby number an input?
So the Rossby number is not an input parameter, but it's effectively a combination of parameters. So
Yes.
for these models, it's probably
something like very small, but
when you think of turbulent flows, you're thinking of that U dot grad U or the V dot grad V term, that vector part of the inertia, as being a leading order term in the dynamics.
then
Here,
some
it's small.
somewhat we can turn off the Coriolis force, then
The magma ocean is probably affected by Coriolis. It's probably what's that? Why does it? Because the vigor of convection is much more vigorous. I mean, what's happening in the core is you can only cool as fast as you can only convect as vigorously as you can get the heat out. To get the heat out of the core, you have to get it out through the mantle. In a magma ocean, the only thing that's preventing you from cooling is your ability to radiate heat out through an atmosphere and get it the Rayleigh number in net motion
Yeah.
might be 10 to 30, something like that.
Yeah.
It's pretty vigorous. And so you get so vigorous that actually inertia becomes important. So
Yeah.
in principle, the answer is yes.
Yeah.
You could dial in the dimensional
Yes.
integrity
Yes.
of the ocean.
I want.
It's not going to work.
I
Because you
yeah.
get kind of resolution. Remember those images that I showed you of the sun?
Yeah.
So that's turbulent convection. Remember how that's slightly complicated because the scale head at the bottom makes those scales really small. But the point is you need a huge spheroharmonic expansion to be able to capture the scales that are going to develop when you have that kind of vigorous rapid turbulent convection.
Why do we use such a low Rayleigh number if it's
Because
That's a limited.
First, the Rayleigh number in the core is probably lower. And also we can't do the low number.
But still, we can't use this real Rayleigh number for the core. So we still have the big problem for the discrepancy between real Earth and Earth core and the simulations. No? So yeah, so we don't can apply the infinite spatial resolutions and in the model.
what is the realistic Rayleigh number in the core?
For 10 power to 24, 5, something like, yeah. So it depends on how much super adiabatic heat flux or temperature gap would be.
The viscosity is so low in the outer core.
It is.
Yes.
So what do you think? So
Yeah.
think of the temperature difference across the mantle as being maybe what we use in aspects, maybe 2,500 degrees, maybe 3,000 degrees. The temperature, superadiabatic temperature across the core might be less than 1 degree Kelvin. So it is very low viscosity, but the driving force is very small. And the reason is that it's being driven at the rate that the mantle allows the heat to escape. That's the problem. So it convects as fast as the mantle will allow it to lose its heat.
And probably, and we also didn't say anything about the scaling. So here is near very close to the critical value. It's 5 times. Yeah, not yet. Shall we move on? Yeah. Has anyone finished the simulation? Are you still learning?
So who's still running?
Okay.
Definitely need to talk.
Yeah. But yeah, probably we can do some things. Yeah, let's stop the simulation with control C. Yeah.
It would be possible for us to actually maybe not take those solutions to full completion.
Yeah.
And in the GNU plot, you just won't have as many numbers in your plot, so you'll come in a little bit earlier.
Yes. And so let's see. I forgot. Yep. So it's a data institute by the GNU plot. So first, we'll use a data file with nusselt.dat.
We'll make sure everyone can get into those final spots.
Can you?
Everyone got the nusselt.dat.
Has everyone found? Okay. So if we look at the inside of the nusselt.dat with a more command, it's simply text file, time steps, time, inner core boundary, nusselt number at inner core boundary, and nusselt number at the outer core boundary. Very simple. So probably, Sean, can you open nusselt.dat with a gedit? Oh no, sorry, nusselt GNU, average nusselt GNU. Yeah, it's a script to calculate the time average of the nusselt number. It's very simple script with 2 lines. Oh, what's wrong? Can you show? But so can you show this script itself? Yeah.
Run it or show?
Show. Yeah. Oh no. More is fine. Yeah, gedit. So it considers these two commands. Plot, probably you've seen plots in Eric's tutorial, aspect tutorial. So plot Nusselt number at the command boundary, column 2 and 4 with lines. And here's the new stuff.
So, Hiro,
Yep.
I ran the first initial one without changing the parameters and control C out and then ran a whole run again. And it just kept writing to the same Nusselt like that. So I have an extra little tail in front. So it still works for me, but if they feel
I see. I forgot to tell. So Calypso always add results at the end of the output file. Yeah, so that's some facts I always learn again and again. Then so sometimes I overwrite the original data. Then I leave it. Then yes, I forgot to tell. If you try to run too much lines, please move the data into some subdirectory. I'm sorry for it. Yeah, I completely forgot. Yep. So it draws a time history of the Nusselt number with lots of time changes, and I also made a plot with a time average between 0.4 to 8. Can you show the script again? If your simulation hasn't completed, change here. Fit from 0 point to somewhere end point of your simulation. Then this script can run. Yeah. So if you are your job still running with to 0.6, can you change 0.8 to 0.8? And then so this script can work for your model. Yeah. And yes. This guy is for 10 power to 100,000 case. 1 times 10 power to 5. Yeah. And average Nusselt number is written in a command boundary.
And I guess the other thing that came up too, the one on the bottom, right? That's the correlation coefficient, right?
Yes. Yes.
Don't be thinking that that's the dimension.
Yeah, right. So here's the correlations, and that's purely one, but it's the solution is just based on the final set of the parameters.
What is the x-axis versus the y-axis on that plot?
Oh,
What is on the x-axis versus the y-axis?
x and y-axis. X-axis is the time. Y-axis is a Nusselt number. Yeah. So sorry, it's very. I don't set any labels on this plot. And I just found a table mistake, table thing. I found a table thing. Here's a table. Table of the solutions. So now we plot the Nusselt numbers, and solution would be 1.95 to 3.37 for these Rayleigh numbers. Did you get these such kind of solutions for Nusselt numbers?
You should be able to look up there and compare your results.
Yeah. Yeah, great. If you, yeah.
So you now dynamo model.
Yeah. Yeah. And same things is for kinetic energies. Kinetic energies, here is it. So kinetic energy is also calculated by this GNU plot command. Oh, here. There is. Sorry, it's kinetic energy is stored in power volume dot, and so you can get a solution with average K GNU with a GNU plot. And so it also makes a kinetic energy plot as a function of the kinetic energy. And the average value is obtained here. And previous slide. So here's a solution of the SPH power volume dot. So it's a time history of the mean square data. Time step, time. I don't talk about it, but toroidal kinetic energy, toroidal kinetic energy, total kinetic energy, mean square temperature, mean square toroidal vorticity, mean square toroidal vorticity, and total mean square with the total vorticity. These are written in one file as a time history. And then, so 2 and 5 columns for the time and kinetic energy.
I mean, for the same reason that Carolina was talking about the distinction between toroidal flow, which is instrumental, versus the buoyancy-driven flows, which is colloidal flow. Sometimes it's nice to just decompose those components of flow the same way that
See.
So,
Yeah.
sort of keeping those things is useful, right?
Yes, right.
In some ways, what we're looking at for the
Yeah.
energetics.
Yes. Yes, yes. And so toroidal components directly driven by the buoyancy, and toroidal flow is generated by the Lorentz force or Coriolis force. Yeah.
I mean, the other thing in standard mantle convection,
Yeah.
it's hard to get. What Lillian said that it's very hard to get toroidal flow because you need very small viscosity variations and other things. In the context of these problems, because you've got the Coriolis force, these two things are very tightly coupled, and so you get lots of toroidal flow by virtue of having the Coriolis force play a role. In interplay with the buoyancy. So you get I don't forget what the ratio is, but they should be pretty comparable.
Yeah, it's comparable. So sometimes toroidal component twice as large as a toroidal, but still same order. Yeah, we had a long discussion, but now something that's conclusions. Oops, I don't have the movie. Not LGS, LC. So here is something like an example and of the toroidal and toroidal component. So toroidal velocity has go outside at a positive value and go inside in a negative. And toroidal flow rotates around these positive and negative patches. So then something rough image, positive toroidal scalar indicate a radial velocity, and for the toroidal component, positive this value indicate a radial vorticity. It's a very rough, not strictly correct, but feasible images. Yeah. So has anyone got kinetic energies? It should be these values around here, from 15 to 26,000. And then, so if we collect this data, so scaling plot will be in this graph on the slides. And it depart from the higher Rayleigh number because we don't have enough spatial resolution. That's the main reason. Yes, right. Yep. Okay, and so I also leave an example for the image dynamo. If you are interested in, try it tonight and yeah.
So sorry if I missed this, but
Yeah.
you specified the boundary conditions.
Yes.
But is the initial condition just the temperature distribution?
Yes, and I also put a small perturbation for the
So that
temperature.
they have a velocity at time 0.
Velocity is at 0, non-velocity.
Just the temperature.
Only given a temperature perturbations.
Okay.
Yeah.
So the other thing I was going to say was that if you wanted to actually use the dynamo model, say, for one of your projects, you might want to put it on your own computer. And if you wanted to do that, then probably you should do it in the next couple of days and make sure that you get Hero to give you a hand if you have any trouble with it.
Yeah. All right, thanks. It's time for coffee. Right. Yeah. Oh, but thanks,